Previously, we have studied the three-dimensional wave equation. The simplest of three-dimensional waves are these plane waves. So let's see what are these plane waves. So, before finding out what plane waves are, let us first find the equation of a plane which is perpendicular to a vector k and that passes through a given point P0. So in this diagram, you can visualize this situation. So this is the vector k and this is a given point P0. So we want to find out a plane that is perpendicular to this vector k and that passes through this point P0. So this is the plane that we are talking about. Now, in order to find out the equation, let us define the position vector of P0, which is this vector, with R0. You can also see this vector R0 from the side view here. Now, let's take a random point on this plane, maybe this one, which we may call P, and denotes its position vector with R. Then the vector connecting P and P0, which is this vector, we can call this R minus R0 vector. And this vector is perpendicular to the k vector. So we can write that the dot product of this R minus R0 vector with k is equal to 0 as they are normal to each other. And if we rearrange this, we get the dot product of R with k is actually equal to the dot product of R0 with k is equal to a constant. That means for any point on this plane, this equation holds. So this is the equation for a plane which is perpendicular to the vector k and that passes through a given point P0. Now let us consider a few planes which are actually perpendicular to this wave vector k, like these planes in the figure which are perpendicular to this wave vector. Now all these planes can be described by using this equation, r vector dot k vector equal a constant, where this constant takes different values for different planes. Now we can also express r vector and k vector using their components along x, y and z directions. Then this equation takes the form k1x plus k2y plus k3z equal some constant, where each constant generates a different plane. Now that we understand that the dot product between the wave vector and the position vector gives us a plane, let us now try to interpret this equation. Let's consider a special case where k and a have these components along x, y and z directions. Now here the k vector has component 1, 1, 1 in all the three directions. So it makes an equal angle with xy, yz and zx plane, and the angle is 45 degrees. So this k vector will point in this direction. So for different r vector, this k dot r will give us different planes which are perpendicular to this wave vector k. Now the electric field E will be parallel to this vector A, as this is a constant for a particular plane. Now we know that cosine of some angle varies from -1 to 0 to +1. So for some plane, this electric field will point in the direction of this A vector when this is +1. When this is 0, the electric field will be 0. And when this is -1, the electric field will be opposite to this direction of A. Now, for our particular problem, we have A dot K equals 0, as you can calculate. So here, A vector is perpendicular to this K vector. That means this A vector lies along the plane. So this electric field should lie along the plane for this example. Now, what happens when we add a time-dependent term in this equation? Say, for example, this equation, where t is time and omega is the angular frequency. Well, then this electric field will change with time at a given plane. So this is an equation for all the planes where electric field is changing sinusoidally. This is what we call a propagating plane wave. The direction of the propagation of this plane wave is the direction of the vector k. Now here, the electric field will be parallel to this E0 vector. So we can call it a polarized wave, where the direction of polarization is this E0 vector. We can also define the wavelength of this wave to be 2 pi over the magnitude of this wave vector k, and also the angular frequency to be omega. Now we can consider a particular case where E0 dot k vector is equal 0. That means E0 vector and k vector are perpendicular to each other. In that case, the electric field will vary in the direction perpendicular to this k vector. We call this kind of waves the transverse waves. Okay, now this equation of plane waves can be expressed by using complex variable. In complex notation, a propagating plane wave takes this form. So, plane wave is the simplest example of three-dimensional wave. And why do you call it plane wave? It's because at a given time, all the surfaces on which the disturbance has constant phase form a set of planes. That's why we call them plane waves. And these planes are generally perpendicular to the direction of propagation of the waves. And we have seen that this is the equation of a plane wave. Now, the contours of maximum field of a wave is known as the wavefronts or phase fronts. In case of a plane wave, these wavefronts or phase fronts are planes. These wavefronts extend all over this space and they travel at the speed of light. You can see the wavefronts of a plane wave in this figure. The wavefronts of a plane wave are equally spaced. They are a wavelength apart. These wavefronts are also perpendicular to the direction of propagation of the wave. Now, you can actually visualize these plane waves by using animations. First, go to this website, then select plane waves from this list. Here you go. This is a propagating plane wave. And you can adjust the parameters and change its orientation and see how it looks from different direction.